Energy of the transition?
Yes. So when we do absorption spectra, we need table with at least two types of data points: transition energies and oscillator strength. So transition energy shows how at which energy system absorbs light, and oscillator strength shows how efficiently it absorbs. Let me ask you then, which information do we need to get absorption spectrum?
Absorption spectrum. You surprised me. Okay.
I surprised everyone. We were discussing for like 10 minutes, trying different options.
Okay, so we need the energy between the transition states.
Yes, good.
Okay. And what else? And we need to solution for the orbitals.
Probability for transition, which we call oscillator strength.
Yes. Yeah. Oscillator strength. Oscillator strength and the energy. Yes.
Yes. So, and there are multiple transition energies and multiple oscillator strengths because there are so many transitions that build this spectrum.
Yes.
Now, the goal for next month in lectures or whatever we left from the semester will be to look for a specific theory that is designed to predict these two elements with improved precision. So the name of the theory is time-dependent density functional theory. So you know density functional theory, and now you add words time-dependent in front of it. And right now, I want to
time-dependent.
Time-dependent.
Is it just the time-dependent Schrödinger equation version?
Yes and no. Well, I don't know if I'm doing the right thing for free discussion instead of showing slides, but yes, derivation of this theory uses time-dependent Schrödinger equation. And no, the time-dependent density functional theory doesn't have time dependence. This is a big confusion. Kay, you raised hand?
Yes.
Yeah.
We plot several times density DOS that graph. So before that was not time dependent. So it's so it was dependent on what? So
it is another confusion. So density of states, I know the words create confusion. Density of states and total density are different things. Density, density functional theory is not because of density of state.
Okay.
It's like same words for different concepts. So you shouldn't associate them. Good. And there is another little misconception. If you hear the name of the theory that we will study for next 3 weeks or whatever month, density functional, time-dependent density functional theory. But in calculation, there is no time dependency. So it's only relates to the way how it is derived. Okay, so the goal for next month is to how to compute transition. I hear myself. No, I don't. It was interesting feedback. So the goal is to, for any molecule, compute all possible transition energies and corresponding values of oscillator strength.
Yes, I did. So I wanted to ask, time-dependent DFT. What you said, it helps us to understand two elements. What two elements? What are those two elements? I missed that out.
I'm not sure if I understood. So what do you mean? Under the words elements, I meant components, the transition energy and oscillators and oscillator strengths.
Okay, yeah, that's it.
Did it answer your question?
Yes.
Okay, yeah, thank you. I will start slowly approaching our goal. So same as we spent about a month for DFT, we will spend some time for TDDFT. It will be not immediate. So slowly but surely getting concept. But before we start, I want to make sure that we have the correct concept and we understand what to expect. We are completed manual on VASP, and we have several lectures like single excitations, and then we will try to get the flow chart for time-dependent density functional theory in the same way as we did for other theories. So the 2 lectures ago, we considered explicit expressions for functionals, how the energy is converted into, how the density is converted into energy, or the potential that one does have in the gradient square plus potential gives us Kohn-Sham orbitals and energies of orbitals. So this potential is the functional derivative of energy, and it's also often calls exchange correlation. And we noticed it's in the simplest way, it is rho to the power 1/3. So there is a group of researchers who are designing explicit expressions for energy as function of density. And for this activity, they have certain abbreviations. So if during your career you will need to read papers related to explicit expressions for functionals, they may use some standard notations in their community, and they are here, like density, Fermi energy or Fermi wave number, which is related to Fermi energy. The gradient, which is used for generalized gradient functionals. Thomas Fermi energy that we discussed almost a month ago, density to power 5/3. There is a way that characterizes kinetic energy, and there are terms for spin exchange if in the simplest approximation. And here are the spin polarizations that we discussed a week ago, right? So density alpha minus density beta divided by their summation. So I think it is the last time you see it in the course, but if you open a paper that shows explicit expression for functional, then you can quickly revisit it and at least get an impression that you know where to look and how it is connected to the material of the class. And here is the functional example GGA functional that we considered a week ago. So it has this.
Excuse me, Dr. Killen.
Yes.
Can I ask just one question about this slide? So the local kinetic energy density, it's in summation over I, the state, but it's local. I need just to understand. Now it's local and summation. I cannot really understand what that meaning for this.
Yep. I'm fine. I have a clear thought and answer. I just combine words into sentences. So, if we practice standard Kohn-Sham procedure, then we separate kinetic energy differently. We just apply gradient square to Kohn-Sham orbitals. But there are advanced approaches where kinetic energy is, well, it still relates to symbol theta, the orbitals. So why it is local? Because the gradient here, it is not function derivative, it is regular derivative. dd dx, ddy, ddz, right? So vector of derivatives. And this gradient computes derivative of the wave function or orbital. I'm making an error that I do not want you to do. So wave function and orbital are different concepts. We shouldn't mix them. So it uses derivative of the orbital locally in the orbital does depend on position of electron in space. And this derivative is computed in the vicinity of this point in space. It doesn't include integration over all points in space. It doesn't compare value of orbital in far points. So local in the sense that we use standard derivative. Definition of derivative as a limit when this increment in space goes to zero, right? Summation here runs over different orbitals. So there is no contradiction. Local in space and summation is in just list of orbitals.
Yeah, that makes sense.
Okay.
Yeah,
okay. So, and now I will, yeah. And here is just inverse sine is function inverse to this one, and one can expand it into the Taylor series. So just to how to understand this equation if one needs it. So in practical life, we likely do not need this expression, but if any of us decides to rewrite the code for DFT, one may need explicit expressions for functions. I know one student in DSU who did it. Dian Mikhailov from physics, he took this course almost 10 years ago, and about 3 years ago, he, as a way towards his degree, he is now completed. He rewrote a DFT code just for fun. Okay. End of DFT, start of DFT functional theory. So there are some verbal formulations of our goals that we describe in a dialogue form, but one can split all computational methods on two classes: those for ground states and those for excited states. And now we go to the area for excited states. Yes, Kaya?
Professor, you showed some equation. Can you go to that page again, that slide, the previous one? Yeah. So the last one, direct exchange energy density. So can you could you please explain that one in a little bit in a sentence? No, it's like equation.
So I'll need to refer to equation, and then I'll say in a wordy sentence.
Yeah.
Density gives us the potential for Kohn-Sham equation. So those the Kohn-Sham orbitals depend only on one electron.
Okay.
But, and in the auxiliary Kohn-Sham universe, electrons do not interact to each other. But the functional and the potential in this equation are made in such way so they keep an imprint, they inherit electron interaction. So that when we construct total energy, using of the total density constructed of these orbitals, we will include electron interaction. And electron interaction has three components: Coulomb when they repel, exchange when they attract, and correlation when they rotate around each other.
Yeah.
Coulomb is positive, exchange is negative, and correlation is something crazy. So the minus sign here means that it is exchange.
Okay.
So it is a stabilization factor, same as in Hartree theory. Part of electron interaction that stabilizes multi-electron system, and it originates from Pauli's screwing principle.
Okay.
Make sense?
Yeah. So another question comes in. So it shows just only exchange one. So it neglect the other parts.
No, the chart, the table here, is not an answer to any practical question. It's only auxiliary tools. So suppose we are clients, we are users of those people who design functionals for us. Suppose we want some theoretical derivation and we need to implement it in a new code. Then we ask a person who derives functionals to give us a formula, and then we implement it into a code. So since equations for functionals are typically very lengthy, in class we considered simplest ways of like LDA, which is like one symbol or one line. But typically, if they're published in papers, they're like multi-line equations, and one uses shorthand approximation abbreviation. So like X. This one is quite simple. So if you see equation like this, we need to understand what X means. So we go to the table and see, okay, X is gradient of density divided by density to the power 4/3. And if we look further into more advanced functionals, they will include some or all of this terminology. So it's kind of dictionary. There was, I need to stop share to see the chat line because someone was typing. Yeah, Boston, if you need to depart, it is fine, and we are already over time. And I will show a couple of slides more, but I will recite them later. Okay. So we need excited state methods. And here, maybe since we are over the time, I will just tell few words more. So we will very slowly approach the TDDFT, and today there will be nothing of TDDFT. It will be only very slow transition. Who did present Fermi weight? Sarah?
Yes.
Okay.
Yes.
Yeah, thank you. So here I'm summarizing once again what is Fermi weight. Oh, Kea now is giving. It's like a judge who takes oath to become an American citizen. Okay, it's interesting background. Super. So, density is composed of orbitals, and typically we take summation over all occupied orbitals from 1 to HOMO. right? Everyone agrees. Now, we can modify this equation. And in this equation, we put number 1 here in front of each pair, in front of orbitals. Here, orbital I, orbital I. Now, we can replace this HOMO to infinity. But in order to put equal sign, we will set occupation factor, which will be 1 if number I is below or equals HOMO, and 0 if it is above HOMO. So with this trick, first line and second line will be equivalent. Please confirm if you are fine with it or not fine, or if you need more explanation. Sarah is fine. Lina is fine. Kia? Fine. Lola? If you do not want to switch on camera, you can use this. Oh, I see. More. Okay. So theta 1 absolute value square. And it depends on R, but I will be lazy and will not write this dependence on R every time. Plus theta 2 absolute value square. And suppose we have only 2 electrons in the system. Then we have nothing else, right? If there are 2 electrons, then the total density will be summation of the part charges for the first and second electron. Now, I can artificially put here the third orbital, theta 3 absolute value square. But in order to have equal sign here, I put theta 3 multiplied by 0. And here I can put theta 1 multiplied by 1, theta 2 multiplied by 1. So it is a little mathematical trick. I can add as many orbitals as I want, but in order to keep the same result, I will multiply them by 0. Lola, is it fine? Or okay, good, thank you. So the factor F here is either 1 or 0. It is 1 for occupied orbitals and 0 for unoccupied. So the letter F originates from the last name of the scientist Fermi. And you may, Lina, did you hear the name of Fermi in other classes?
Yeah, yes.
Fermi-Dirac distribution, right?
Yeah.
And Thomas Fermi theory in our class. So this settings when this F equals 1 equal or below HOMO and 0 otherwise corresponds to Fermi-Dirac distribution for 0 temperature, and it corresponds to ground state. 1 electron in occupied orbitals, 0 in unoccupied. Now, what does Fermi weight do? What the skill that Sarah taught to us? So move this little circle here and the other one here. So in the regular trivial way, one can say Fermi weight 1 for all occupied, and 0 for all unoccupied. So if I add Fermi weight, and then I need exactly count how many orbitals do I have. So like here I should put as many ones as many orbitals. If I have 33, 32 orbitals, I need to put like 1, 1, 1, 1, 1, 1, 1, 32 times. And then 0, 0, 0 as many times as many empty orbitals. If I use this command, it will change nothing. So I put it in the in card. It will reproduce ground state calculation. So it's a little silly to do. But there is an option. If I write this Fermi weight string and I replace one of the occupied orbitals with 0. Oh yes, yes. I think I'm finishing now. 0 and put 1 here. It will correspond to promoting electron from one occupied to one unoccupied, and then it will be very approximate description of the excited state. Okay, enough. We are over time. Many thanks for investing time into this material. Everyone is welcome to disconnect. I'll try my best to share the recordings.
Thank you, Dr. Klein.
Yes.
Have a good day.
Yeah, you too. Thank you, sir.
Dr. Kellen?
Yes.
For the Fermi, as I remember, we were studying like the probability of the fermions as electrons can be considered as fermions to occupy the orbitals because it's obeying the Pauli exclusion principle.
Yes, it is the same.
Oh, okay.
And VASP software allows to manipulate this distribution. So it can compute it. There are some keys that will make this Fermi distribution according to the temperature, or we can manually manipulate it.
Yeah, I remember it was a term in the equation that related to the low temperature, that it has like the system at low temperature and getting that energy could be occupied. The distribution would be related to that.
Yes, there are. If you change the temperature begin, temperature end, it will change electronic temperature, and it will make this distribution slowly changing near the gap. Yes, yes, correct. So I will not go further because I'm over time. But if there are some questions, I'll be happy to answer. Let me quickly show a chart on the project. The plan for research projects is very unique and specific in each case. And if we agreed on something personally, do not listen to me right now. So I'm trying to bring some very common suggestion. So like if you do not know what to do, if you didn't talk in person, then it is something that may be as a good starting point. So if you completely have no idea what to do, this flow chart is like a backup plan for research project. So what is shown here? First, one needs to draw a model, select a model, and it can be a single molecule or it can be absorbed of like molecules A sitting on a substrate, or it can be like component of several things. Then, for no matter what you do, one needs to optimize geometry, and we were briefly talking about it in the lab. I apologize, I didn't share recordings. I plan to do it later. I just have some issue with the computer, but I'll resolve it during the weekend and share the recordings of lab in today's lecture. So after you draw a model or import it from the database, you need to make sure that it is optimized. And in previous labs we were not focusing attention. Now one needs to do optimization with several steps. And if this step confuses you, please talk to me. The not non-optimized models often give strange results. Now, process and characterize your model by making density of states and spectrum for optimized geometry. And if you got training in chemistry, then these two steps can be identified as synthesis and characterization. Synthesis and characterization. Now, after you have your model in optimized geometry, you create new directory and heat it to a temperature that you design based on your scientific intuition. If you have no idea what to do, try something ambitious, a little bit higher than room temperature, like or substantially higher, because then you see some interesting dynamics. But you may try different temperatures. So remember, for VASP, create new directory for each new calculation. Otherwise, VASP will override your files. After heating is done, run molecular dynamics at given temperature, and at the end of the molecular dynamics, take the cont car, convert it into postcar, again in new directory, and do again DOS inspector. And then you will have, in the minimalistic way, you will have two density of states and two spectra. One before molecular heat treatment, before molecular dynamics, another after. And then you can compare them to and describe by your scientific intuition and by words what is the difference. So basically, how the system responds to thermal treatment. If you do these minimalistic steps, you will be good enough to successfully complete the course. Okay. Of course, one can speak a lot about shortcomings and restrictions of this approach. For example, some students in previous years immediately raised hand after these words and told, like, it's not a good scientific question because during molecular dynamics, system takes multiple configurations and you offer us to take only the last one. Yes, it is a correct statement, but it is only introductory step. If I ask you to characterize several snapshots along trajectory, it will be too much for a course. So we just on one hand. On another, if your model experiences formation or breaking of a chemical bond between compounds due to thermal treatment, then density of states and spectra will change dramatically at the end of the trajectory. For example, before the treatment, it can be wide open gap, and after density of state, and after heat treatment, it can close the gap completely. So it can convert from insulator to metal, or it can just perform catalysis and create new compounds. So this is not ideal, but it is a minimalistic background set of steps that will guarantee success in the course and optionally help you in the success in your research. And beyond this diagram, we should talk in person because there are specific features of each project. And here again is very generalized table. I'm not inviting everyone to do the same. It's only a food for thought. So suppose you have one model. Suppose you have it in neutral, spinless ground state. And then you can thermalize, do molecular dynamics, density of states, absorption spectrum, do dispersion with K points, plot orbitals, like all characterization that you learned in the course. After that, one again, so do not consider what I'm telling as a must. It's only a suggestion what you can do if you want to research. It's very research is always a creative procedure with indefinite direction and indefinite answer. So doing one or another way may or may not bring to success. But if you have no ideas what to do, it's only some options. So then you can take your model, excited by survey that I think that Sarah presented at the end of her presentation. Yeah. And then with this Fermi excitation, Fermi weights, to thermalize, to do molecular dynamics, and then to do density of states, spectrum, dispersion, plot orbitals. I easily imagine myself on your side, and I will develop an irritation against instructor at this point because like he's asking us to do so much. No, I will hate the instructor. I will not do it. So I'm not inviting you to do it immediately or to do it at all. It's only options. Okay. So you decide what to do and what not to do. And another. So I'll finish it and then you discuss. I see there were raised hand from Kia, and I see raised hand from Lola. Is it for last question or you have new question?
I think it's for the last question.
Okay. Then you can remove the like lower hand. There is a button in Zoom to lower hand. Okay, so one can then do another set of directories and make neutral spin polarized ground for I spin equals to spin. And then again repeat the whole procedure of like thermalize, molecular dynamics, density of state spectrum, K points, orbitals, and observing how those characterization changes for different configurations, one can learn a lot about system. Your time and your intellectual effort is a precious resource. So before doing one or another numerical experiment, think twice, maybe consult with me. So do not spend too much time. Again, I'm just showing opportunities. It doesn't mean that everyone needs to do the same. We are not robots, right? And then one can also look for anion to withdraw electron, the number of electrons, remove, add electron, and repeat characterization. Then cation, remove electron, again repeat characterization. So for some models it will be really beneficial, and I have some comments for which project it will be more important, for which it will be less. But just take it as food for thought. Okay. Are there any brief questions? No? Okay, I take it as no question. Oh, okay, yes?
Yeah. So, Professor, there you wrote lifetime. What's the lifetime means there? Maybe you didn't show us that thing.
Yes, I didn't show. So, it's too early. I do not want you and me speak about it, but during the remaining time, I'll tell what it is. So, briefly, for your curiosity, if you have ground and excited state, And by now we were approximating them, but as HOMO and LUMO. But
Yes.
very soon we will see a little bit deeper view on this thing. So if you excite and you have an electron on LUMO and no electron on HOMO, after some time, after tau life, there will be spontaneous emission. The electron will relax back to the ground state, back to the home. And this lifetime, tau life, is approximately equals to 1 divided by oscillator strength for this transition, with some additional factors. So if your research is related to light emitters, chromophores, something green fluorescent protein, light emitting diodes, then this is important. If your model is not dealing with it, then you don't care.
Okay.
Enough?
Yeah.
Yeah. Thank you for the question. Okay. And now I'll quickly go over slides, but I think main thing was our discussion.
Dr. Killian,
Yes.
I just wanted to clarify something.
Yes, please. And you can, if the microphone is not working well, you can quickly type. Or speak whenever is comfortable for you. I noticed that you want to clarify something.
Yes, okay. Yeah, sorry, I had my friend here. So I just wanted to clarify what lifetime is. Did you say is the time it takes to go from the excited back to the ground state?
Yes, exactly.
Okay, all right, thank you.
And for your project in the class, it's not as important, but for your rotation project, it could be relevant.
Okay.
Okay.